thing will start moving in a circle. And so the obvious question is, well, how big is the circle? How long does it take to get around the circle? How depends on maybe how fast it's going, what its charge is. We can do this quantitatively. And it's not that complicated to do quantitatively. So you know it's circular motion. Right? So it's circular motion. And so you know the acceleration is going to be equal to the magnitude of the acceleration vector is the velocity squared, magnitude of the velocity squared divided by r. And in fact, we're not going to do it now, but it's not super hard to derive that if you have a vector that changes like this, the rate of change of this of the velocity vector is equal to its length squared divided by the radius of this circle. Right? You just basically count how long it takes it to go all the way around and divide, and you'll get this. So it's not like some big fancy complicated thing. It's just geometry that gives you the rate of change of this vector going in a circle is the velocity squared divided by the radius. Okay, so that's circular motion. And what we know is that if it's going to move this way, if it's accelerating inward, there's got to be a force inward, which we know is the magnetic force on it, right? When it's here, V goes that way, B is into the page, V cross B is left. And so the force is always perpendicular to its motion. And so that is the force that's holding it in this circular path. And so the force is just going to be the mass of the particle times v squared over r, where v squared means the velocity vector's magnitude squared. And we know the force on the particle is, well, it's going to be q times v cross b. So q times the velocity vector crossed with b. And v and b are perpendicular. So q times v vector cross b vector. But in all cases going around this circle, since b is into the page and v is somewhere on the surface of the page, v and b are perpendicular. So this just becomes q times the magnitude. Magnitude of the force is going to be magnitude of v times magnitude of b times sine of the angle between them, which is pi over 2, 90 degrees. And that's 1. So the force is q times v times b. And the acceleration, and the force needed to hold it in a circle is also m times v squared over r. All right, questions so far?
No, that's pretty good.
All right. So fine. So now what we know, let me just continue this way actually for a minute. So good. If we know this, now what we know is that QVB has to equal mv squared over r, right? The mass times acceleration has to be equal to the force. So QVB is mv squared over r. So now it's pretty straightforward from here. This tells us that the radius of the circle is, just cancel this out, is mv over qb. Okay. So it's interesting to think about for a second. If you double the speed of the particle coming in, then the radius of the circle it will travel around is twice as big. If you double the magnetic field, it'll be half as large a circle that it travels in, which makes sense, right? It pulls harder on it, and so it forces it into a tighter circle if B is larger or Q is larger. Okay, so good. So that's the radius of the circle. Period, which we'll call tau, the time around the circle. Well, that's not very hard. That's just going to be 2 pi r over v, how far it is around the circle, which is 2 pi r, divided by the velocity is the time it takes it to go around. And then just plug in for r, mv over qb. And if you do that, you get 2 pi m over qb. All right, so that's the period, that's pi. So that's the number of seconds it takes the particle to go around the circle. So there's something funny in this. The time it takes to go around the circle is independent of how fast the thing is moving. Right? It depends on, that's just a number, it's just a constant. Depends on the mass, the charge, and the magnetic field, and that's it. The period, the time to go around, does not depend on how fast the thing is going. And you can see why, because if the thing is going twice as fast, then of course that you would think, well, it's going twice as fast, it should take half as long to get around. But if it's going twice as fast, the radius that it has to travel in, it will also be twice as big. So they exactly cancel, and you have the time, the period around is independent of the speed of the particle. And that actually has huge applications, and we'll talk about this more in a little bit. Hold on. Is that the mass of the charge? M is, yeah, ASA, M is the mass of the charge. Right. And this actually has a lot of applications in that so most particle accelerators, circular particle accelerators function on this property. And so early particle accelerators, you could have a magnetic field that pointed into the page. And you could have charged particles. And if you fire them in, if they're fired in here, they'll start to go in a circle. And as they gain speed, they will, they'll go in larger and larger radii as they gain speed. But the time that it takes them to go around doesn't change. And so early particle accelerators could work by having, you could have this thing. We're not going to go into huge detail about this. You could have this side be positively charged, this side be negatively charged. So if you imagine basically these hollow, sort of almost horseshoe-like things, this side negatively charged. And so you could accelerate particles across this gap. And then the magnetic field would keep them moving in a circle. And you could switch, and you would switch the polarity and make this minus and this plus to pull them back across here to keep accelerating them. And you didn't have to worry about the fact that it might take it longer to go around the circle when it was a larger circle than when it was a smaller circle. There would be a fixed frequency at which you could oscillate this, and you would stay in sync with when the particle came to the gap ready to be accelerated across it. Because the time that it takes to go around really doesn't matter how big a circle it's traveling in. It would stay the same as it expanded. And eventually there'd be a gap somewhere in here, and you could fire the particles out of the field altogether once they reached a maximum radius. So modern accelerators don't function this way, but there are simpler designs to get larger energies. But at least early accelerators took advantage of this fact that the period was independent of how fast the particle was moving. Okay. And then, of course, if this is the period around, the frequency, which is known as the cyclotron frequency, is obviously just 1 over t, which is qb over 2 pi m. Okay. Okay, so think of questions for a second.
Real quick on the bottom, I think I missed that. F, what is F and why does it equal that?
F is frequency.
Okay, frequency. Thank you.
So I should have written that, right? So just the number of loops per second that it makes is obviously 1 over the time it takes to make one loop. Does the charged particle have own B field. No. The charge particle, the short answer is no, right? Because the charge particle, if you are standing, Greg, that's a trickier question than you think. But so for us standing, if you're flying along with the particle, then you don't see any charged particles moving, right? According to what this charged particle sees, it just sees itself as a charged particle, and then it's in a B field. Now, there is a trickiness about the fact that we, standing on the ground, we say, well, I see a charged particle moving. And what we're going to learn is that, well, moving charged particles create B fields. But when we talk about the Lorentz force, we're not talking about the B. There's no self-induced force from the B field created that the charge creates, then inducing a force on itself. Okay. Is that okay, Greg? And then Jade, M is the mass of the particle. So it's a particle of mass M and charge Q. Okay. Okay, so this Lorentz force and this curling of charged particles into circles comes up in a huge range of applications. So modern accelerators, from X-ray machines to particle detectors to mass spectrometers, all use this basic idea. So this is an old picture from a particle detector. What you're looking at is the results of electrons and anti-electrons coming in at opposite directions and colliding, and in the center of a detector that looks like a barrel. Most modern physics experiments use detectors that are sort of shaped like a barrel. And you have particle oppositely charged, or sometimes same charged particles, coming and colliding, converting their energy to mass. And then you have heavier particles that decay, and it's how we learn about quarks and leptons and fundamental forces of nature. So when they collide at the center of this barrel, then all the decay products come flying outward through the barrel, and there's various electronics throughout the region to detect what were the masses, what were the charges, how fast were they going, how fast they were losing energy to help us identify what kind of particles they were. And what you're looking at is actually these lines are drawn by software reconstruction, but what you really have in this barrel is a lot of detectors use a whole bunch of long strung wires pointing this way. And then as a charged particle passes near them, if the region is filled with usually some kind of gas, and they ionize the gas and leave a trail of electrons behind them. And so what you really see is this curved path was estimated from a bunch of little dots of wires that showed that a charged particle passed near them. So the other thing you notice is that all these paths are curved. And they're curved because there's a B field, there's a giant solenoid, and we'll learn about solenoidal B fields. There's a coil of wire wrapped around the detector that makes a B field that comes, give me a second. I'm doing QB cross B in my head. V cross B, no, the B field goes into the page, and I'll show you how I knew that in a second. So there's a B field that goes into the page from some current that's run. And so if I have a positively charged particle produced at the collision origin and is flying straight out, then V is going this way, B is into the page, so V cross B is going to be that way. And so this charged particle is then going to travel a little that way, but now the force on it is going to change direction and always be perpendicular, and it's going to curve this positively charged particle into a circle that's, well, too big to fit in this region, but it's a piece of a circle. And so this positive 0.62 in units that we're not going to talk about for now, but it gives basically a measure of the particle's momentum, and the sign gives you the charge. So we know this is a positively charged particle because it curved this way. And by measuring the radius of curvature of this circle, you can see, you can tell basically how fast it's going, how much energy it had. And when you look back, and this really comes, it's not a whole lot more complicated than really just this, right? The radius is mv over qb. Q tells us what we know from the orientation of the circle. You notice this one has a negative sign. We know this is a negatively charged particle, and it's a higher speed particle because it has a larger radius of curvature. R, the radius of curvature, is larger. Right? In fact, it's the momentum that's larger, but essentially it means it's a heavier and or faster particle if it has a larger radius of curvature. So you can see, right, the straightest track looks like this one, right? And so it is a negatively charged particle with high momentum. And then in fact, some of them are low enough momentum that they just complete circles, right? So this is one common way that this is used. Mass spectrometers use this too by you fire a. We might do this example in detail later, but if I have all right, so first, sorry, questions on this so far? Isn't that paper for an overhead projector? Yes, it's an old sheet of paper. A says the reason I don't think I was using my left hand. I hope I wasn't. Right? Yeah, I don't. Was I? Shoot. In which, if I was, hang on. Now I have to see if I did this whole thing backwards. Asa is very awake this morning. I don't read my syllabus, and I don't know my left hand from my right hand. So if B is coming out of the page, V is this way, B is coming out. Now, I think I used my correct hand, right? If V is going this way and B is into the page, V cross B is that way. I might have had my left hand here, but I think I'm using the correct hand. Right, so V is that way, B is into the page, V cross. I think it's just, the way these shelves are set up where I'm standing, I can't get to the right place. So it's V is that way, B is into the page, so V cross B is, it's easier actually if I turn it this way. V is this way, B is into the page, so V cross B is that way. If for a positive charge particle. For a negative charge particle, QV cross B would go the other way because Q will flip the direction. Yeah, I don't know about overhead projectors. I was happy to see them go. Left-handed people never liked overhead projectors because the ink would always wind up on your hand. So I was very happy to see them disappear. Okay, so the same thing happens in mass spectrometers, right? If you have a charged particle, if I have a charged particle flying through here, and we're not going to do this one in detail, I just want to show you another sort of application of this. Right? Let's say if I take a charged particle and I fire it from here through this and try to hit through that opening here, so this is a wall with a hole punched in it, that's not going to work because obviously this particle is going to be deflected, but there'll be a force on it and it'll be deflected like this and it'll hit the wall there, right? And you know the force on this thing, the force to the right is going to be Q times E. Whatever the E field is, depends how much charge you have on these walls. So there will be a rightward force on it. And then you say, okay, well, if I make a B field that goes into the page, in addition to this E field, actually take a second on your own and figure out, I want to make a B field that is going to push this particle the other way and let it fly through this opening. So I want you to take a minute and figure out, what way do you want the B field to go? This way, that way, down, up, in, or out. Figure out a direction for the B field so that this thing will make it through that opening. All right, so just take a second and work on it on your own. Don't put it in chat yet, though. Okay, I don't want to do a poll. Just somebody pipe in. What directions do you have? Yep, good. Yep. If I put a B field that is into the page, so if I have a B field into the page, then the force to the left, right? Because if the B field's into the page, if this is a positive charge particle, V cross B is left. So force left, and V and B are perpendicular to each other. And so the force to the left will just be Q times V times B, because sine of pi over, it'll be times sine of pi over 2. So that'll be Q times V times B. So if this thing were to go through the opening, so to hit target, in other words, and then you can just have a detector here that detects whether or not your charged particles are flying through. To hit opening, you need QVB to equal QE. Right? Okay, so fine. So now that can tell, so the ratio of these two things tells you the velocity of the particle. Right? So mass spectrometers and velocity selectors basically work on this principle. So you would have something where you might have a fixed magnetic field and have some adjustable voltage, that you would tune this voltage until the particles made it through the target. And now you've balanced the magnetic and electric forces, which are pushing in opposite directions. And then that gives you the velocity is equal to E over B, the ratio of the strength of the field in newtons per coulomb and the B field in Tesla gives you the velocity in meters per second. Right? Okay, so questions so far? Okay, continuing our brief tour of the Midwest. If you fly over sort of south of Chicago, you'll see the largest particle accelerator in the U.S. I think this is I forget how many miles around. When you're flying over, don't think aliens made some crop circle somewhere in the soybean fields in Batavia, Illinois.
Not an alien circle, it's a people circle.
Yes, it is. It is. So what you're looking at here is the largest particle accelerator still functioning in the U.S. The largest particle accelerator in the world now is in Switzerland, which U.S. is involved in, but the largest U.S. accelerator still is in Batavia, Illinois. Yep, CERN. So this is somebody Google search miles circumference Fermilab. Because I don't want to quote the wrong number. And then as soon as you Google search that, then stop all Google searching and other surfing. But that's a good thing. So what you're looking at is, right, so this is a proton antiproton collider. And so what you're really looking at is just a road. And then below that road, underground there are magnetic fields, what's called dipole magnets, all the way around this ring. 3.9 miles. Double check that, Trevor. That seems short. That's supposed to be a circle. All right, well, I guess it is. I thought it was longer. I'm used to thinking CERN, which is, I think, 17. Okay, so what you have is throughout this, so underground, you have a pipe and a tunnel. The tunnel is, the size a small car could drive around it. And then all along the pipe are what's called dipole magnets with the create B fields that go inward, downward. Incidentally, top quark was discovered at this accelerator, the sixth of the quarks. So if you have a proton going this way, and so what you look at here is what's called a linear accelerator, and so protons are accelerated with oscillating electric fields, are accelerated down this long straight. It's called linear accelerator, and then they're injected into this circular accelerator. And in the circular accelerator, there are dipole magnets where the field points downward. And so if you have a positively charged proton going this way, and it's in a magnetic field that goes into the page, I said it wrong. Protons must be injected the other way. Antiprotons must be injected this way, so that you get, so if antiprotons come in this way, so you have something with a negative charge. So if you fire something with a negative charge this way, V cross B is outward. So Q times V cross B, if it's a negatively charged particle, would be inward. So antiprotons, or P bar, are fired this way, and protons are fired the other direction into the accelerator. And they both accelerate in opposite directions. And then we're not going to get into details, other magnetic fields, more complicated magnetic fields throughout the accelerating ring cause the particles to weave in and out past each other, except at the site of detectors where the magnetic fields steer the particles into each other so they collide at the center. But they're all of this, although it's complicated engineering to get it to really steer and focus beams of charged particles, but it all basically functions on QV cross B. Okay. Yeah, right. Slide, right. You can't do that it's a feature, not a bug of transparencies. All right, so think about questions for a second before we go on. Okay, so let's do one simple example of this. And actually, before we do this example, we have to talk, this drives me crazy. We have to talk about a simple unit, electron volt. First of all, how many, one electron volt, those of you, certainly everyone in chemistry knows this. One electron volt is how many joules? Either type or unmute.
Is it 1.6 times 10 to the negative 19 joules?
Yep. One electron volt is 1.6 10 to the minus 19th joules. Okay. What's the charge on an electron in coulombs?
I don't know this one.
All right. Well, you're in a class of well over 100 people. Somebody needs to help you out, Eric.
Is it negative?
It's 1.6 times 10 to the negative 19 coulombs.
Yeah. It's 1.6 times 10 to the minus 19th coulombs. It's a miracle, right? The conversion factor from electron volts to joules is exactly the same as the charge on the electron in coulombs, right? And I don't know I forget what movie this is from. It's not Alien, but right, there are no coincidences. Right. Why is that? Well, it just follows from why you define this unit in the first place. If I take a 1 volt potential difference and I take a +1 Coulomb charge, let's say this is positively charged plate, this is a negatively charged plate. So there's an E field there, and I take a charge of +1 Coulomb right here, and I let it go, it's going to be accelerated across that gap. And when it gets to here, how much energy does it have? When particle, this is one of these things that's not very mathematically sophisticated, but is subtle, but it's important. So 1 Coulomb particle falling through a 1 volt gap. How much energy does it have when it gets there?
One electron volt?
Nope.
Joule.
Yeah, what? I think I heard it. What?
Yeah, a joule.
Yeah, a joule. How many joules? 1, 7, 11? This is what happens, Liam. You answer a question, and the punishment is you get asked more questions.
A 1 joule?
Yeah, it's 1 joule. Because 1 volt means 1 joule per Coulomb, right? It's this unit that is, I keep nagging about, that you have to have a physical feel for. It means that there is 1 joule, a 1 volt gap means every particle, it takes you 1 joule of energy to move 1 Coulomb push it from there to there. Or if you let it go, it'll pick up 1 joule when it falls across. If this is 1,000 volts, and I let a 2 Coulomb particle go here, a +2 Coulomb particle here, and it's 1,000 volts potential difference between these two things, it's going to accelerate. And when it hits here, its energy will be 2,000 joules. Or said another way, it would cost me 2,000 joules of energy to push 2 coulombs from there to there, because 1,000 volt potential difference means it's 1,000 joules per coulomb of difference between those two sides. And I'm not moving 1 coulomb, I'm moving 2 coulombs. Okay, so questions so far?
So does the electron volt come from like work in a sense? Like when we learned about capacitance and you asked like how much work does it take to move this? Is that all we're doing in a sense with electron volt?
Yes, yeah, right. So we're going to get there. So now the next question. So we just found that 1,000 volts at +2 Coulomb charge, it falls across it, will pick up 2,000 joules of energy. So now the question is, what happens if I take an electron, say this is minus, this is plus. I guess if I start it here, I'm going to have to do work to push it from there to there. If this is an electron, because it's negatively charged, the E field goes this way. And so the force on an electron is that way. Okay, so the electron's charge is 1.6 times 10 to the minus 19th coulombs. And if this is 1 volt, which is the same as saying 1 joule per coulomb, how much energy does it cost to push this many coulombs from there to there? Well, it'd cost me 1 joule if that were a full coulomb, but it's not a full coulomb, it's only this. And so the energy needed is 1.6 times 10 to the minus 19th joules. That's how much energy it costs to push an electron from there to there, or how much energy I get back if I let an electron fall from here to there. When it smashes into this wall, it'll have that many joules of energy. Okay, fair enough. That's nothing new. It's the same as this and that. It's just a different amount of charge and a different voltage. You can keep changing those around. But this happens so often of electrons, things with a multiple of the fundamental unit of charge falling through voltages, that we make up another name for this amount of energy. We just call that 1 electron volt. It's the energy that one electron will pick up if it falls across 1 volt of potential difference. Right? So it's no coincidence that these two things are the same numerical factor. All right. Just works. Todd Howard. All right, I'm gonna have to ignore chat for a little while, or get a haircut. I actually don't know who that is. I probably should, but anyway. Okay. So questions so far on this? What is across from energy when particle hits wall? What is across? Oh yeah, 1 Coulomb. Yep. All right, other questions so far, either chat or just unmute? All right, good. Okay, so let's look at a simple case of, you work on this one for a few minutes. We're gonna have, let's say we have 1,000-volt difference, 1,000 volts between these two plates. I take an electron, or let's say I take a positron, so E plus, and I accelerate it. And so I let it go here. This is the positively charged plate. There's a hole there, so it's going to be accelerated across, fire through that, and it's going to come into a region where there's an inward going magnetic field. And once that happens, it's going to move into a circle, which is either like that or like that. So you take a second and draw on your page, right? Figure out if from once it hits this, so it's going to be accelerated across. It's going to have some velocity when it comes out of here. It's going to go into this region of a B field, and it's either going to curl that way or this way. So take a second and figure out which way. Just see how people are doing. All right, it'll either curl into a circle that's up or a circle that's down. So just vote on one or the other. All right, we're about half and half, which makes me concerned. So, all right, so think about this. So it's a positively charged particle. Think about it when it's right here. Its velocity is this way. B is into the page. So the force on it is Q times V cross B. And so V is this way, B is that way. And so V cross B is up. Using your right hand, V cross B is up. So this thing will be curled into a circle that goes up. So it's going to move like this. Okay. Questions on this? Anyone not see this or need help? Okay, so good. So it moves in the circle. So the question is, find the frequency. Okay. Basically, how many loops per second will this thing make? So we're going to go back to what we did before. All right, so we know that the force on it is Q times V times B. And we also know that the mass times acceleration of it has to be equal to m times v squared over r, where this r is the radius of the circle. So again, this is just rederiving what we did before, equating force and ma. Let's just set these two things equal to each other, which gives us mv squared over r is qvb, right? And then that tells us that r is equal to mv over qb. Okay, so what we really need is, though, to figure out the radius of this circle, or the period or anything else, we're going to need to know how fast this thing is going. And what we know is that when it comes out of here, it has 1,000 electron volts. right? The energy is 1,000 electron volts because it's something with the charge of an electron that fell through 1,000 volt potential difference. So its energy is 1,000 electron volts, which you can convert. And that's equal to 1.6 times 10 to the minus 16 joules. So that's the energy that it has in joules. And now what we really want is its velocity. Well, we know that 1/2 mv squared has to equal 1.6 times 10 to the minus 16 joules. So then just plugging in mass of an electron or mass of a positron, which is the same, this gives, so just plug in that mass, do the arithmetic, take the square root, and this should give you a velocity of 1.9 times 10 to the 7th meters per second. Okay, once you have that, so we're not going to go through all the arithmetic. You can do this. Plug in the mass of the mass of an electron or positron, 9.1 times 10 to the minus 31 kilograms. Velocity, which we just found, Q is 1.6 times 10 to the minus 19th coulombs. And B, which somebody needed to tell you, and I neglected to do that, is, let's say, 50 micro Tesla. 50 10 to the minus 6 Tesla. All right, so if you plug in radius of mv over qb, you should get 2.16 meters. So I'm assuming you can do the arithmetic, just I'm giving you the numerical answer so you can check it on your own. You should get 2.16 meters for the radius of the circle. The period is 1 over the period, which is about 1.4 megahertz. So 1 point will make about 1.5 million laps per second. Okay, so think about questions on this, on that problem. I mean, it's fairly straightforward, but think about if anything is odd to you on it. What do you say B was again? So B is 50 micro Tesla going into the page. I forgot to write it when I first wrote down the problem, and then we got to it here. I realized I didn't write it down when I needed it. Okay, what else? Other questions? Okay, so the last thing that we do in this chapter, sort of the last thing we do in this chapter, is finding the force on current carriers. So basically, the force on a wire carrying a current in a magnetic field. And if you think about it, it makes sense that there ought to be a force. If I have a wire, so I just have some wire carrying a current I this way, and let's say I have a B field that points into the page. So you just have a, a wire you hooked up to a battery, and it's carrying current that way, and there's a B field that goes into the page. And you think, well, why should there be a force on a wire just because it carries a current? Well, what you already know is that the force on charged particles is Q times the velocity vector crossed with the magnetic field vector. All right, but this current is made up of, and we always remember our convention, we always think of the current as positively charged carriers, even though in principle it's electrons going, say, this way in a wire. We think of electrons going that way as the same as lack of electrons going this way. And so we assume positive charge carriers all moving in this direction, the direction of the current. So I labels the direction of positive charge flow. Okay, well, each of these is moving with some velocity like that. And so there's a force on every one of these carriers, which is in the direction of Q, which is positive, times V cross B, which is left. So there's a force on this wire as drawn that is that way, from the force on each of the charged particles that make up the current that's going like this. Right? Okay, so the question is, how much force is it? I mean, what do we use for Q or V or B here? Right? We don't know Q and V, and for a wire carrying some current, if you measure a wire has 3 amps in it, I don't know what those are. But we can find that from this. So the force, the total force on this, let's say this section of wire that we're interested in, that's in a B field, has a length of L. So the force total is going to be Q times V sub C, which is the velocity of the carrier, times B times number of carriers. Right? So this is the total force on this wire. You just have to know how many carriers there are in this section of wire. And what's Q, how fast are they moving? The charge on each carrier, how fast they're moving, and the strength of the B field that they're in. And we don't have to worry about the angle because it's V is going this way, B is into the page. So Q, V cross B turns into Q times V times B times sine of 90 degrees. So that is the force on each of the carriers, and this is the force on the whole wire. Okay. And what we know, though, is that I is equal to dq dt, right? The rate at which charge is flowing, the rate at which charges are crossing some, let's say you imagine a wall here, the rate at which charges are flowing across it, dq dt, is the current. But that's going to be equal to Q times the velocity of the carriers times number of carriers per length, right? Right, the rate of change of Q across some boundary is Q times their speed times how densely packed they are. And so we first did that with this water pipe analogy, and related the current in a pipe to how fast the water is moving. Okay, but now we can use this thing. This tells us that number of carriers, so just doing arithmetic tells us that number of carriers is going to be I times L divided by Q times VC. So that's pretty handy, because if carriers is IL over Q times V, and we substitute that in here, this tells us that the force is going to be equal to Q VC B times I times L, substituting this, over Q times VC. All right, well, now Q and VC cancel out, and that leaves us with I times L times B. So the total force on this wire in this arrangement is going to be I, the current in it, times L, the length of the wire, times B, the strength of the B field. And you can show, we're not going to show this, but in general, you can show that the force is equal to I times L vector cross B vector. So in the case where, so here, if the force, or sorry, if the B field is perpendicular to the current, the force on this wire is I times the length of the wire times the strength of the B field. If they're not perpendicular, let's say you have the wire going like this and the B field is not coming straight into the page, but sort of coming like this angle, then the force on this wire will be I times L cross B. And there's a little bit of a funny thing here, and I'm following what your book does so as not to, I think it's confusing if I do follow a different convention than your textbook. But in my mind, it's current that really makes sense as a vector, right? It has a magnitude and it has a direction. Your book and some things don't follow that convention. They say the length of the wire itself has a vector direction. And you think, well, what the hell is the vector direction for a piece of wire? Well, it's a vector whose length is the size of the wire and whose direction is the direction that the current is flowing. So it doesn't, in actually solving a problem, it doesn't really matter whether you put the vector, whether you said, I would prefer, don't write this down, but just to understand it, to me, it makes more sense to say it's L times I vector cross B vector, because I naturally feels like it has a vector to it. But your book doesn't do that. They just assign the vector to B, and Survey does too. So either one you're using. The wire has a length of L and a direction that's the direction of the current. Okay. Okay, so think about questions here for a second. Okay. You sure? Everyone all right? Okay, we still have a few minutes. Good. Okay, this is not, we're going to do a simple example and then a more complicated one. So the first simple example we'll do is, let's say we have a, so here's X, Y, you take a second and figure out what direction Z goes. X goes this way, Y goes that way, both on the surface of the page. Figure out the direction of Z. Right, you want a right-handed coordinate system. So X hat cross Y hat needs to be Z hat. So if X is that way, Y is this way, X cross Y. So Z is out of the page. Z is coming out toward you. And let's just say that we have a wire of length half a meter. And it's carrying a current of half an amp. And let's say there's a B field in the direction, a mix of J and K. And so it is pointing kind of into the page. So B vector is equal to, let's say, 0.03 J hat. Really, I should say Y hat. Plus 0.01 Z hat Tesla. Okay, so the current is going this way. Okay, so we need to find the force on the wire. Okay, so we want to find the force in the wire. So the B field is a mix of y hat and z hat, more y hat than z hat. So the B field's kind of pointing this way, has no x component, only y and z. So the B field's going like this. The current is going like this. And so take a second before we actually do this. We know the force on the wire is going to be I times L vector cross B vector. So take a minute in your head and figure out the direction of L vector, which goes that way, and B vector, which is a mix of y and z, which comes this way. So just in your head, picture the direction of L cross B. L cross B. Right, so I think it'd be right. This L is that way, B is this way coming up. And so L cross B is kind of going this way a little. I know that it has to be perpendicular to both of these. There are only two directions that are perpendicular to both this and that. It's this one and the other, and the one pointing back inward. And so I'm only using the right-hand rule to choose between the two. Okay, good. So we have this. So we're just going to do, in this case, I'm not going to try to find some opening angle between this and this, right? I'll just, although in this one, it actually wouldn't be hard to do, but let's just do it out anyway. So force is I L hat L vector cross B vector. So force is going to be 0.5 X hat cross sorry, I screwed up. F vector is I, which is 0.5 times L hat, or sorry, L vector, which is 0.5 X hat amps crossed. So this is I, that's L, crossed with B vector, which is 0.03. Sorry, let me change these numbers. I wrote down the number wrong, and I want to make sure I get at the end. It's 0.003, sorry. 0.003 and 0.01. Okay, so I need to cross this with 0.003 y hat plus 0.01 z hat. Okay, so I got to do this cross product out. And if I do that out, I'm going to get, right, I'll get a 0.25 times 0.003. So I have two terms. X hat cross y hat is z hat. And x hat cross z hat, x cross z should be negative y hat. Okay, so if I do that cross product out, I will get, is this okay? Hang on. I'm going to write this out and then see if it makes sense. I'm worried about something. So if I do this, I should get minus 2.5 times 10 to the minus 3 newtons y hat plus 7.5 times 10 to the minus 4 newtons z hat, right? Because x hat cross y hat is z hat, and then x hat cross z hat is negative y hat. And then it's just a matter of multiplying those together. Is the z component for B supposed to be positive or negative? The z component for B is positive. Although there is something I'm worried about the signs of this. So give me a minute. So you look this over and then I'm going to look it over too.
I don't think that's going to be 7.5.
7.5, 10 to the minus 4.
Yeah, I don't think that's what it would be.
Maybe not. It's possible I can't multiply either. Sorry, I got to stop my phone from ringing.
And could you explain more about y hat and z hat, how we get that part?
So this comes straight from what the magnetic field is. Right, so this part is given. And so if you have I goes this way, so it's purely x hat, and then, okay, maybe it's all right. So then the B field has a mix of y component and z component. And so the cross product of this cross that points this way. And so it has a vector that points this way, which is the cross product, has a positive z component, right? Because z comes out of the page, and a negative y component because y points this way. And then the only question is whether or not I multiplied correctly, which I might not have.
No, you did. I see. I didn't actually distribute the other 0.5 in yet, so that's why.
Oh, thank God. Usually it's me, but I guess in this case it is not. Yeah, right. Because you get x, y, and this is the one that turns into a z. 3 10 to the minus 3 times 0.025. So, okay, I think that's all right. All right, so think about questions on this for a second. So the B field, Daniel, the B field is coming out of the page, correct? It has a bit of, not purely out of the page, but it has positive y and positive z. And so it's more positive y than z. And so it's sort of leaned this way a little, but it is coming somewhat out of the page. Z positive is out, Greg and Daniel. Can you state specifically which numbers were multiplied by which? Because I'm trying to, some stuff and my numbers don't agree. This whole thing, 0.5 times, so you can just pull that out and do it at the end. So then we'd have this cross this, which would give you 1.5 10 to the minus 3. And then x hat cross y hat, that gives you z hat. So this times that goes here. And then x hat cross z hat is minus y hat. And so this times this is what winds up there. This times this, then of course the whole thing multiplied by that winds up here. So for more complicated questions where the vectors aren't just going in one direction, the right-hand rule is only useful for checking our work. Correct. Yep, Christina, exactly right. So we didn't need the right-hand rule for any of this, right? We just did the cross product and the components will work out. It's just, I wanted to make sure I didn't screw up because something looked funny. And so I was by hand also checking that L vector cross B vector, yeah, is a vector that has a positive Z and a negative Y because it points cross product red cross orange is this way. Positive Z, negative Y. Right? Yeah, Daniel, it's hard to tell, right? I mean, the way you draw it, especially my drawings, I probably should have, I don't know. 3D drawing is not my strength. Even, let's face it, 2D drawing is not my strength.
Wait, I can show you my diagram. I'm good at drawing things.
Are you? Nice. I should have you like
No, you probably
to me. I'll use your
well. There you go.
One-dimensional drawing I'm actually quite good at. 1D drawings I can do. All right, so any questions so far? We're sort of running over, so we should end. Yeah, I guess if you labeled some stuff 0, the calculations would also work for perpendicular. Absolutely. Yep, if you're purely perpendicular, you can do it the same way. You'd just get 0 for the other components. You'd get like an x hat cross a y hat and everything else would be 0. So Alistair, yes, that's right. Okay, I think that hits all the chat questions. Okay. All right. Have a good day, everyone. See you on Thursday.
Goodbye,
Have a good one.
everyone.